Hi, and welcome everybody to this presentation of our latest Xpress release, 8.11. Today, I will introduce the changes and prominent new features in this release. As you might be aware, FICO Xpress optimization consists of various components, all built on top of each other and nicely integrate within each other. At your organization, you might enter this stack that we see here at different levels. I, for myself, work down here in the lowest level, on the heart of Xpress, the solver core. Today, I would like to tell you what news and new features there are to make this heart be getting stronger than ever. Let's go! Us developers in the solver team have three main drivers: performance, features, and robustness. These are the things that we work on in each and every release. First and foremost, we strive to make our wide variety of optimization algorithms and solvers for various types of optimization problems faster and faster with every release. Secondly, we want to make your life more convenient and open new optimization applications by offering new modeling capabilities, enhancing analysis tools, and other useful features. And finally, we always aim to further improve our solver's numerical robustness, with Xpress already being the most deterministic and probably the most robust solver. The main focus of this release is MIP performance. We have news from the restarting feature that we introduced in 8.9 and two new ways of exploiting parallelism within the solver. We now allow probing independent of cutting planes and branching, which leads to some performance improvements. We have continued working on piecewise linear and general constraints, which also is a feature introduced in 8.9. In this release, we improved the remodeling of these constructs when they are reformulated as MIP problems. My favorite project was about robustness. The solver provides a prediction of the solution process robustness before the solve. Pretty cool. We will also talk about some significant changes in our nonlinear solver, or rather pre-solver. And finally, we will look at how all of this affects performance numbers and why 8.11 is the fastest Xpress ever. Let's start with restarts. As mentioned, we introduced the ability to restart the branch and boundary in the 8.9 release. It addresses the fact that some MIPs can be solved with relatively small search trees without much effort, while others require large trees, even when you throw your heaviest machinery at them. In traditional MIP solves, you solve the initial AP relaxation, then go through cutting and heuristics to tighten the DUIT and primal bounds. When you believe you have done your best in tightening the problem, you enter the branch and bound search, where you keep going until the problem is solved to optimality. Note that it is often possible to use information discovered during the tree search to further strengthen your formulation of the complete problem. For example, the solver can use improved MIP solutions to tighten bounds globally. However, this late tightening of the complete problem will never be exploited by the root-exclusive strategies. Another issue is that the most critical branching decisions are those taken at the start of the tree search, which, unfortunately, is the point where we have the least information available. The basic idea of tree restarts is to first perform a partial tree search with some light settings, addressing MIPs that require few enumeration, and then, at some point, restart from the beginning. In the second pass, you can use the information discovered and collected during the first pass to strengthen the complete problem and make more efficient branching decisions at the first nodes. Moreover, the fact that we reached the restart point during the first search suggests that the problem is more challenging than expected. Effectively, we use this technique to classify the given problem as an easy one, which can be solved by a single pass, or a hard one, for which a restart is necessary. Hence, in the latter case, the second search is executed with a different tuning of a solver corresponding to a heavier strategy required to face the problem's complexity. Obviously, a vital aspect of the strategy is the question of when to restart. To make it efficient, you should avoid restarting when the search is actually close to being finished in the first pass, since this would essentially mean doing all the work again and doubling your runtime. Hence, before triggering a restart, one should be sure that a significant amount of time is still necessary to terminate the search. Thereby, we will ensure that only a small percentage of the overall search gets lost after restarting. Then, by making the vast majority of the search more efficient, we can gain performance. This brings us into a tricky situation. On the one hand, I just argued why we do not want to restart too early, but for the very same reasons, we also do not want to delay the restart too long. The longer we wait to restart, the more considerable the amount of work thrown away. The trick, essentially, is to predict as soon as possible whether the given problem is hard and needs a restart or easy and can be solved in a single search. In this release, we have introduced a tree completion estimate, which approximates what we need to know for our restarting exercise. How much of the complete tree we explored so far? More precisely, the amount of tree search completed is represented by a monotonously increasing value between 0 and 1. You can understand this as an estimated percentage of search completion. It is 0 in the beginning and 1 when the search is complete. The idea consists of assigning a value to each node of the tree, which is split between the two children after branching is performed on it, starting with value 1 at the root node. The basic criterion for the split is to divide the parent's value equally between the two child nodes. More precisely, proceeding from the root node, each time we create a new node, it is labeled with weight corresponding to half of its parent's value. Then, when we prune a node, its weight is added to the tree completion estimate. Here we branch on a node with weight 1/2 and split it evenly into two children with weight 1/4 each. Another branch, and if one node is cut off, we add it to the completion estimate. We branch again, and if now both child nodes are cut off, we add them to the estimate. So at this point, our running completion estimate is 1/2. In practice, we do not split a parent's weight evenly, but rather weigh the child nodes according to our internal estimates of their relative bound change. However, the completion at the beginning might not be a reasonable estimate for a very unbalanced tree. Therefore, internally, we use the rate of change, so to say the first derivative to predict the tree size. In any case, the tree completion estimate, as I just introduced it, is made available as an attribute to the user. Details on this new measure can be found in the linked technical report, of which one of our developers is a co-author. Since Xpress 8.11, we use this tree completion change rate to decide whether it is worth restarting. Does our completion measure grow rapidly and we expect to finish soon? Keep on going with the current path. Has it gone stale at a low rate or only increases very slowly? Restart rather sooner than later. That's not the only change that we did to the restarting feature, but the most prominent one. Additionally, we refined the interaction of the first and the second pass to carry more information over, learn from it, and throw less work away. We also did a few tweaks to the strategies applied before and after the restart. We tested restarts on our internal MIP performance benchmark set. It contains a bit more than 1,100 instances tested with 5 permutations. A little more than half of the problems are solved entirely on the root node. About half of the remaining instances will have a sufficient tree size for a restart to be interesting. We can observe that the most impressive results come from problems with huge trees. The larger the tree, the more significant the benefits from restarts. However, improvements are also made for many problems with small trees. As already mentioned, we will apply a more lightweight strategy that allows us to walk through small trees faster. I would like to point out that there is no need to disable callbacks when using this very dynamic strategy. All existing callbacks support tree restarts. No inconvenience here for our users. Another nice feature that we have introduced for the MIP solver is solving entire nested MIPs within our main MIP solve. Indeed, it is now possible to create a new problem and solve it while we are still solving the main problem. In a sense, we have always had this ability as part of our heuristics. For example, we have a local search heuristic that creates a reduced MIP, solves it, and returns it as a heuristic solution for the main problem. However, before this release, the reduced MIP had to be solved as a single task and could not be interrupted, and it could not be broken up or run on parallel threads. This is possible now, and we will show 2 examples on the next slide of how we can use this for some cool features. Within our parallel task scheduler, we can now switch between different nested MIPs. This means that we can do some work on one of them, then work on another one, return to the first one, and finally go back to the main source. In this way, we can balance our computing resources and use them where we think they are most needed. This strategy works with both opportunistic and deterministic mode. Of course, the solution of these nested MIPS supports all the usual features that can be controlled independently: cutting, heuristics, and standard branch and bound. In particular, the nested MIPS request the number of threading resources they need from the parallel scheduler, which looks at all the requests received and grants the resources to the MIP with the greatest need, for instance, by giving priority to the MIP with the largest gap. There are, however, a few limitations. One of them is that these nested MIPS do not yet support callbacks. Hence, the user can't guide the branch and bound or generate cutting planes. The use of callbacks would disable this feature. Moreover, the new restarts that I talked about before are currently incompatible with nested MIPS. This is a technical detail that we hope to overcome in the next releases. Okay, so far for the technical setup. I promised you 2 applications, and here's the first of them. In our new Xpress release, we apply this framework to problems that consist of several separate components. If a problem contains variables that do not connect through direct or indirect constraints, we can partition the problem into components without overlapping constraints. The solution to one component will be completely independent of solutions to other components. Thus, we can solve each component as a separate MIP. There is a major performance benefit from doing so. The complexity of solving the full problem as a single solution process drops from being the product of the tree sizes of the component MIPS to being the sum of the individual efforts. Although a modeler could always identify and solve each problem individually, it is not always convenient to do so. They would have to invest effort into identifying when this happens and extracting the component problems. It is also possible that only pre-processing reveals that the problem discomposes after dropping some connecting constraints. For 6 years now, we provided a pre-solving feature that would eliminate minor components within an easy solve and fix as part of pre-processing. The problem with larger, or better, harder to solve components is that you don't want to solve them sequentially because you will not have a feasible solution until you have found a solution to each and every component. So ideally, you want to solve the components concurrently. And here, our new support for concurrent nested MIP solves comes in handy. Each component is set up as a separate MIP, and they are all solved concurrently with the most resources automatically allocated towards components with the largest absolute gap. We could identify several instances with a considerable number of components in our internal benchmark sets, even after applying our component pre-solver. Let's look at some performance numbers with this feature in particular. For hard instances, measured as taking more than 100 seconds, the speedup was more than a factor of 30. Again, this is a factor of 30 on affected instances, not 30%. Disconnected components, however, are not very commonly seen. Our benchmark set contains only a few such instances. Hence, the overall benefit on the set of all our MIPS is only 1%. It increases to 3% on the most challenging problems. This feature is activated by default. However, if it causes problems for some reason, it can be disabled by setting the new MIP components control to 0. Moreover, as already said, it is also disabled automatically by callbacks. Finally, the disconnected component feature works also if the problem has indicators or delayed rows, but it does not yet work with quadratic constraints. This limitation, again, is planned to be removed in the future. Let's look into this in a little more detail and consider a problem consisting of 8 large independent components as an example of the changes in the log. Before entering the tree search, the user gets a message looking like the first 2 lines, indicating the start of the decomposition search and the number of components found, together with the size of the 5 largest of them. The following branch and bound search will then look slightly different. The heuristic that has found the solution is no longer indicated, since the solution now consists of solutions of the individual components, which different heuristics might have found. Now, just a dash is displayed, indicating an update of the incumbent. In the log, you will notice something else. The solver also prints the amounts of resources that the subMIPs consume. Indeed, since each nested MIP has its own tree, altogether might require quite a bit of memory, more of what is needed by the main problem. In this example, we can also note that the tree completion estimate, which has, at this moment of the search, a value of only 0.026. Another cool use case of our new nested MIP feature is that we can start multiple concurrent solves of the main MIP. With this release, we can start concurrent solves with identical controls but with different random number generator seeds. Each concurrent solve runs for a limited number of nodes. If the problem did not solve, all but the most promising solve are terminated, and only the winner gets to continue, using all available threads. This feature addresses problems that show a high degree of performance variability. The term performance variability refers to a change in performance that we observe after some changes that we would expect to be performance neutral if looking at them naively, like changing the random seed. However, these changes might not be neutral, since random tie breaking might lead to the solver ending up at a different state. Due to the very heuristic nature of MIP solvers and the potentially exponential blowup of branch and bound, such little changes might make a huge difference. For degenerate problems, you will end up at an alternative LP optimal basis, and from there on, cutting, branching, and heuristics will take a different path. Imagine, as a most extreme case, a binary problem without objective function. For such a problem, all feasible MIP solutions are vertices of the LP relaxation. Once the solver finds one of them, the solve will immediately terminate. However, only very few vertices might be integral, but all will be LP optimal. A slight change in the simplex might make the difference between solving the MIP with the initial LP in a few seconds by pure chance or branch and bound running for hours. It is often down to chance whether a particular solution process completes quickly or not at all for problems with a high degree of performance variability. By starting up multiple concurrent solves, you can exploit this variability by having each solve follow a different solution path. This way, you can increase your chance that one of them finishes early. On this slide, we see an example of how the log could change when you use this feature. What is usually considered the tree log now starts immediately after the LP relaxation. Hence, no log shows the number of cuts added and deleted since they are different in each run. What is actually displayed is the master log, which shows the best solution found and the best bound among all the concurrent solves. There are two new columns, the number of rounds of cuts at the root node and the number of running solves, which drops to 1 once the winning solve has been selected and the main search starts. However, you can also see that the number of solves decreases even before the winner selection because one of them has hit the node limit a bit earlier. Again, we allocate the threads dynamically. If one of the solves lags behind, it gets additional threads. This strategy is very effective on dedicated problems, but not employed by default. Let's talk probing. This is where another structural change in our MIP solver happened that benefits performance. So, what is probing? Probing is a technique to learn information about the implications of what happens when binary variables would be fixed, for example, by branching. Precisely, we choose a binary variable, first fix it to 0, apply bound strengthening procedures, and subsequently do the same for the variable fixed to 1. Then we analyze the consequences. In the following, assume that x1 would be a fractional variable in the current LP relaxation. Let's look at some cases of what we can learn by probing. The most extreme case is when both x1 equals 0 and x1 equals 1 implies that the problem would get infeasible. Since x1 has to take one of these two values, we just solve the current subproblem. In a more typical case, if only one of the probing directions is infeasible, then the variable can be fixed to the opposite bound. Assume one of the probes implies a particular fixing for another variable x2, while the other probe implies a fixing to another value or even the same. In such a situation, we can aggregate this information and present x2 in terms of x1. In this way, when x1 is 0, x2 will be A, and if x1 is 1, it will be B. Now assume that the two probing directions imply bounds on the same variable and not fixings. We can use the weaker one as a new bound for the common variable. And finally, the most common case is that we detect single direction deductions and store those in an implication graph, which we later use for cutting or branching. Since cutting and branching are the main places where probing results are used, this is also where we traditionally applied probing. However, as you saw on the previous slide, probing has a value of its own, since it can detect fixable variables or deduce bounds on other variables. We wanted to keep this even when our internal tuning decides to employ cutting and branching strategies that do not use probing. Hence, we made probing independent of those decisions and now call it on every tree search node. The side effect is that probing is now done more often, not only at nodes where we cut. This reduces the branch and bounds tree size, even though it requires more effort, ultimately leading to an overall performance improvement of about 3%. You might remember that we introduced some neat modeling features that allow you to model general constraints like min, max, and the absolute value of variables, logical constraints such as logical and the logical or, and piecewise linear constraint directly into the solver. The solver will then handle them directly. It will linearize and reformulate them as appropriate. In particular, when different reformulations are possible, it will decide which one to use. In the 8.11 release, we have extended the portfolio of reformulations. For example, we added a new reformulation of absolute constraints, using special ordered sets of type 1. This one worked so well that we made it our new default. Of course, for a user, it is possible to make a dedicated choice via a control. Another example are piecewise linear constraints, for which we added a new binary formulation to the standard special ordered sets of type 2. Again, the user can choose between one or the other through a control. Moreover, we have extended the pre-solver for piecewise linear constraints. As you can imagine, there are many more small improvements, and I can only list a few of them. One is the use of fractional symmetries in pre-solve reductions for continuous variables in MIPS. We essentially take our LP folding idea for continuous problems and put it into the pre-solver for MIPS. Another improvement regards delayed rows, which are now added to the problem immediately as soon as they are violated by the LP relaxation solution, and not only by a candidate integer solution. We made a change in the solution of the initial LP after a tree restart. Indeed, with our new restart logic, we perform many more tree restarts than before. Hence, the efficiency of the initial LP solver represents an issue. In the new release, instead of only using the dual simplex every time, we applied concurrent LP solving after a restart if dual simplex was not the concurrent winner in the first pass. We have also added a control allowing to switch from barrier to dual simplex for reoptimizations during LP sifting, after finding out that barrier is superior to the dual simplex in this case. Okay, so far for performance. We will get back to this when looking at performance number at the end of the presentation. Let us now continue with our latest work on solution robustness. Numeric robustness is a crucial feature of the Xpress solvers. Since a few releases, we provide more and more information and features to the users to help them understand and resolve numeric issues that might come up in their models. This includes the learning to scale approach that we released earlier this year. It uses the machine learning model to predict the best possible scaling of matrix coefficients to increase the simplex and MIP solving process numeric stability. Learning to scale led to tremendous improvements for our out-of-the-box performance on numerically challenging problems. We improved all our measures of numeric stability, most of them by a large two-digit percentage. However, there are intrinsically numerically challenging problems where you cannot resolve such issues in advance by scaling, and users want to get informed about this. Here you see two examples of information you get from the solver for a relatively badly behaved instance. The first is a summary of errors that occurred during the solve. The second is an optional feature that samples the conditioning of subsystems that you solve during the optimization and comprises them into a single 0-1 value, the attention level. We usually tell our users that values larger than 0.1 indicate that numerics might become an issue for the model at hand. There are two inconveniences here. First, all of this information is available only after the solve, when the issues already occurred. Second, the most detailed information, which is also the most intuitive to work with, namely the attention level, is a non-default feature because it is expensive to compute. In the worst case, this might mean you let your optimization run for a few hours or even days, Then you get suspicious that the instance might have been numerically challenging and would like to get this confirmed. You activate the attention level computation and run again for a few hours or days to get your report. We thought that can be done better and developed another ML model to predict the attention level right at the beginning of the solve. Probably I should first explain what exactly we mean by an attention level. The attention level measures the degree of expected numeric misbehavior of a MIP instance. To make it intuitive, it is a measure between 0 and 1. Here, 0 means that the instance solves perfectly robust. 1 means you have to expect numeric errors at any point in time. You should not trust the result too much. As I said, the rule of thumb is that attention levels greater than 0.1 deserve special, attention. We compute the attention level by sampling condition numbers of basis inverse matrices throughout the branch and bound search. Generally, a large attention level correlates very well with numeric errors. But as I said, there are two drawbacks. The attention level is only available after the solve, and it is relatively expensive to calculate. And hence we do not do this by default, but only when a specific control is enabled. The goal of learning the attention level was to overcome both drawbacks and provide the user with an indicator of numeric stability that is available at the beginning of a solve, here after the initial P relaxation is solved, and thereby in particular after we learned a scaling, and with an indicator of numeric stability that is cheap to compute. Learning the attention level uses a fast-to-evaluate ML model with readily available matrix scaling features and a new unique feature that considers the conditioning of the matrix with respect to the right-hand side. It approximates the real condition number of the initial P, but it is an order of magnitude cheaper to compute. For the ML experts, in contrast to learning to scale, which used a linear regressor, learning the attention level uses a random forest regression. It turned out that this delivered more precise results. To summarize this slide, in Xpress 8.11, we provide the user with an indicator of numeric stability that is available at the beginning of a solve and cheap to compute. But how good is it in predicting numerical issues? In our experiments, with more than 1,500 test cases, it achieved an accuracy of about 97%. On the slide, you see the confusion matrix. Each row depicts the number of instances in the two predicted classes. Either we predict the matrix has a low attention level or that it has a high attention level we saw before the solve. Each column shows the number of instances in the actual classes, whether the instance ends up having a low or a high attention level after the actual problem solve. Here we can distinguish four cases. The most common one is that everything is okay. Both the prediction and the actual attention level are low. In this case, nothing changes for the user, and indeed, nothing needs to change. The next typical case is that both predicted and actual attention level are high. Well, this is the reason for this exercise. We want to warn the user in such a situation that something seems fishy about his model, and we will now trigger this warning by default in Xpress 8.11. The other cases are false predictions. The less worrying issue is that of a false positive. We warn the user also the model ends up staying below our threshold for deeming a matrix numerically suspicious. The only really nasty case is the last one. We miss warning the user, even though the model ends up exposing a high attention level. Luckily, this happened in only 3 of more than 1,500 test cases. That this rate is so low is by design. We bias the learning algorithm such that it is slightly more likely to produce false positives instead of false negatives, given that the latter ones are worse in practice. Altogether, the model achieved an accuracy of 97%, which is pretty accurate by machine learning standards. And this is how it would now look like in the log. After the root LP solve statistics, we might get a warning about a large predicted attention level. The prediction is run by default. If you do not see this line in your log, then the prediction was that no numeric issues are expected. And as we saw in the previous slide, this is probably correct. Let's hope that this is one of the features you will never see in action, meaning that all your models solve nice and stable. Of course, you can also query the exact prediction value as an attribute. There's also a recent blog post on this feature, which you can find on our community website. There are a couple of other improvements regarding robustness. We now got an iterative solution refiner for quadratic optimization problems. This feature gets rid of violations both in the primary and the dual solution by solving a series of auxiliary problems that represent the residual error of the preceding step. For a more detailed explanation, there is a blog post on our community website. Watch out for Numerics 2, zoom into the unknown. Moreover, we have started to consider numerical stability for creating the starting basis of the dual simplex and for the starting point heuristic of the barrier algorithm. We have introduced iterative refinement within the barrier algorithm to improve its calculations. Finally, we have added a new control to clamps solutions to force them to stay within the bounds. There is another tiny convenience feature that I should mention because many of you might see this in the log files. The log now prints the non-default control settings of the solve so that you can see with what settings the solve executed. This is also convenient for us developers, when we can tell directly from a log how a client is using the solver and provide more efficient support. Our Python interface is pretty mature, so there are no major changes there. But one thing worth mentioning is that it now checks for the license in different locations. This change aligns the Python behavior with the behavior of other solver components. Firstly, it checks the XPauth path. If this is not set, it will still check Xpress, even though this is deprecated. If this is not set either, it will finally look at the standard installation directory. If it can't find anything in the last location either, it uses the community license. Thus, if you own an Xpress license, you should either put it in the standard installation path, that's what we recommend, or if you prefer, set the XPauth path environment variable. Note that if a location is defined by an environment variable, then Xpress Python checks for the license there and skips any other location, regardless of whether it finds the license or not. This is different from previous behavior and in line with the behavior of the other solvers. Okay, we had the MIP solver, we had solution robustness, we had interfaces. Let's now talk about some news from our nonlinear solver. A major change to our nonlinear solver is that pre-solving is no longer a part of the AP approximation solve, but it is applied before it. In other words, we have introduced the ability to make pre-solve reductions on the linear constraints of the full nonlinear problem. And the AP optimizer just needs to apply these reductions. Of course, we still use pre-solving at the approximation level. After all, this is where we get new linear constraints all the time, but we spare the double work on those parts that always stay the same. This change has the nice effect that we can now also allow for more expensive reductions if we only have to do them once. In this process, the nonlinear pre-solver has been made more modular. It can be called on individual constraints on which we can apply stronger linear reductions so that we can get rid of all the redundancies usually found in linear problems. We measured the impact of these big changes in terms of the confined primal integral, which is our standard measure to evaluate the nonlinear solver's performance. The confined primal integral puts the solver running time in relation to the observed solution gap, emphasizing the early part of the solve. In a sense, it expresses finding good solutions quickly is a good thing. Anyhow, concerning the standard measure, we get an improvement of 30% on our nonlinear test set, which is pretty significant. Even better, what we introduced here is just the start. Indeed, we have only worked on the basic continuous reductions. We plan to extend the pre-solver to other kinds of reductions. Together with the pre-solver, we have also improved other aspects of the nonlinear solver. We added better checking of nonlinear expressions. This enabled us to eliminate the slightly complicating and unintuitive way to add formulas and change formulas in the nonlinear constraints. On the slide, you see the traditional way of doing so, requiring access to an internal artificial column. The new way to add or change a formula is a one-liner, much more readable and intuitive. This change comes with many new API functions to nonlinear. We also kept the old ones for backwards compatibility. And there is a control keep equals column if you need to read files in the old mode. Speaking of file I/O, Our nonlinear extension of the LP file format can now not only be used for wiping out problems to inspect them, but also to read problems back in. So far for nonlinear improvements, we kept the highlight of every release presentation to the end. What does the new release perform like? A year ago, we released Xpress 8.8. This table compares our new 8.11 release against 8.8. It is a typical year-on-year improvement table. These are numbers on our benchmark set, consisting of a mix of public and client instances. Client instances are sampled to avoid any type to dominate the benchmark, similar to how MIPLib 2017 was constructed. Mentioning it, MIPLib 2017 benchmark makes up about 20% of our internal MIP benchmark set, with the rest being mainly client instances. We have a similar setup for our LP and nonlinear tests. We see that we got a nice speed up all across the board for LPs, particularly for the simplex algorithms. This is mainly due to the learning to scale feature. We split the MIP evaluation into two sets. The benchmark set, for which we measure time to optimality, and the PDI set, which mainly consists of unsolvable models, for which we measure the prime dual integral. This table shows that our MIP solver for more challenging problems is now about 40% faster to optimality than a year ago. Across all instances, which also include some that are trivial to solve or will be solved by the initial LP, the overall speedup is 15%, which is a very strong value. On the PDI set, we observe an improvement of 16% in terms of prime dual integral across all instances. About 1/6 of the instances do solve it in our time limit of 2 hours. For those instances, we observe a speedup of around 30%, reflected in the rightmost column. I already mentioned that the new pre-solver improved nonlinear performance by 30% alone. Together with some other features, we got a 45% speedup on nonlinear within the last year. Towards the end, I would like to give some recommendations where you can learn more about Xpress and the technology it implements. Check out our community website to learn more, browse the forum, view training material, and in particular, read the blogs. Through the FICO community, you also have access to the Product Ideas portal, where you can submit your suggestions for product enhancement. This is also the place where you can download a community license and start playing with the software immediately. Or, if you are an academic, consider our academic partnership program, which grants you full licenses of all Xpress solvers, given that you work at an academic institution. You can also follow us on Twitter to get informed about the latest news in Xpress. Finally, if you want to get an in-depth understanding of some of the cool features I spoke about today, you can read our papers. Our work on the confined prime integral appeared in Mathematical Programming, and Learning to Scale just got accepted for PWL 2021. And that's it, folks. Thank you for listening to this presentation. If you have any questions on this latest release or on FICO Xpress solvers in general, feel free to email me. Until then, see you.